Hi everyone, my name is Arnaud Delaunoy and I'll present you a crisis in simulation-based inference. Your posterior approximation can be unfaithful. Work done with my collaborators Yuri Hermans, François Roset, Antoine Wenkel, Volodymyr Bengi and Gilles Loup. We will start with a basic introduction to what simulation-based inference is. Simulation-based inference can be used for Bayesian inference based on a simulator that implicitly defines the likelihood. So you can sample synthetic observation from the simulator, and based on those samples, the goal is to build an inference engine that, given a real observation, produces a posterior over the parameters that could have generated this observation. Here we provide examples of approximate posteriors obtained using simulation-based inference algorithm. On the left you have the ground truth posterior, and on the right two different approximations. We observe that the posterior density obtained with the first approximation is sharper than the true density, and erroneously putting most of the density in a single mode. Consequently, it may exclude parameter values that are actually plausible. In this work, we advocate that this behavior is not in line with the scientific method that aim to reject implausible values, since one could wrongly exclude plausible values and drive the scientific inquiry in the wrong direction. A better approximation would be the second one. This one is flatter than the ground truth posterior and hence fail to reject some implausible parameter values, but do not reject any plausible value. To illustrate this, let's consider the case of dark matter. There exists a whole bunch of theories that can be mutually incompatible, and the goal is therefore to exclude implausible theories by making inference based on observation. Consequently, we would like to only reject theories that we are sure to be implausible. However, having an approximate posterior that is sharper than the true posterior could lead to erroneously invalidate some of those theories. So to quantify the conservativeness of the approximate posteriors, we compute the expected coverage, defined as the proportion of credible regions that contain the nominal parameter. If the expected coverage is higher than the credibility level, then too few parameter values are rejected, and if the expected coverage is lower than the credibility level, then too many parameter values are rejected. We then define a conservative model as a model whose expected coverage is higher than the credibility level for all credibility levels. The core contribution consists in a large-scale empirical study of the conservativeness of approximate posteriors obtained from various simulation-based inference algorithms. Here we plot the evolution of the expected coverage with respect to the credibility level. A diagonal line means that the approximate posterior is perfectly calibrated. A coverage curve above the diagonal means that the approximate posterior is conservative, and a curve under the diagonal line means that it is overconfident. The first observation that we make is that all the benchmarked algorithms produce non-conservative approximations on at least one benchmark. This means that all those algorithms could erroneously exclude plausible parameter values and be potentially misleading. Another observation is that this issue seems to be stronger for non-amortized approaches. Indeed, we see that the coverage curve is sometimes way under the diagonal line for those methods. Following on this, let's note that globally diagnosing non-amortized methods is computationally expensive. Indeed, computing the expected coverage requires computing credible regions for many different observations, and in the case of amortized methods, a single model is built and used to compute all those credible regions, while for non-amortized methods, a model must be built for each observation. We therefore advise practitioners to either consider the use of amortized methods or non-amortized methods that allow some local diagnostics to ensure the conservativeness of the approximate posterior. Finally, we perform the same diagnostic for posteriors built using an ensemble of models and observe that ensembles represented by a black curve shows higher expected coverage than individual models represented by a blue curve. Although not guaranteeing conservativeness, we conclude that ensembling constitutes an immediately applicable and easy way to mitigate the overconfidence issue and build more reliable posterior estimators. Therefore, we have advised to use those when possible. Thanks for listening.